Now can you hear me? Now can you people hear me? Can you hear me? Can you see me? So what I was trying to talk about was what are the chapters that are going on right now here, that is modern physics. It's easy and it's scoring also. It is important for JEE mains as well as for JEE advanced, for both. Right? Generally, whoever are going to be having physics as their weakness, they'll pick few chapters in order to make sure that they are going to score 20 to 30% of the marks. And one such topic which the people who are weak in physics are going to pick is going to be modern physics. So that's why, right? So before I start the session, I just wanted to give you that info that yes, whatever chapter we are dealing with is the most easiest one. Even photoelectric effect was easier. I have done it yesterday. Today we will be completing the whole atomic physics. The whole atomic physics will be completed, and then we will move on to nuclei. So are you ready? Can you please say clear? Can you please say clear? If you can hear me and if you can see me, can you please say clear? Aerospace engineer. Sir, I was the one who requested to ignore the comments and I considered. Man, see, I consider everything that is going to do good to you. I consider everything that is going to do good to you people. Okay, fine. Without wasting time, we will start. But just give me a small confirmation. Clear. Okay, Ibrahim has said clear. Navdeep has said clear. Hey, Navdeep, you have come over here. Okay, nice, good. Now, this is the brief thing about me, and then see, we have NVSAT examinations going on online or offline. Please do register. And if you have any siblings like younger sister or younger brother, make sure they are going to be registering this and writing the test. So if they do good, they are going to get a lot of prizes, and at the same time they are going to get 100% scholarship or up to 100% scholarship in the Vedantu offline centers and even the online courses. Okay, fine. Now, what are we going to do in this lecture? That is also important, right? See, Rutherford model of atom. See, I am not going to talk about explaining the whole experiment. There are few important things which I have to give. For example, impact parameter and how the impact parameter is related to the angle of scattering. So these things have a bit of weightage these days. Especially these are mentioned in NCERT, and those values can be easily derived also. Like you can use conservation of energies, conservation of angular momentum. So you can use those things and you can easily derive those things. So generally those are the ones which are missing in the books. Like some books have it. So there is a chance that yes, questions can come from Rutherford model also. So we will slightly go deeper in this. And then almost every book is going to go deep in Bohr's model. So we will talk about Bohr's model also. But after that, I will talk about effect of movement of the nucleus. Bohr's model has taken an assumption, or not assumption, they said that the nucleus is going to be at rest. As the nucleus is very heavy, when compared with the electron, nucleus is assumed to be at rest. That's what Bohr has taken. But reality is that the nucleus is also going to move, right? That they haven't taken into consideration. So what will be the effect of the movement of the nucleus is something which we are going to discuss. And yes, I think in 2014 or 2013, there was a question on that. So that's why we'll talk about it. And then we will talk about atomic collisions, which generally the books are not going to be covering. Generally. Okay, now let's start. Let us start that. Oh, I converted this into PDF, right? So as a result, the animations, you can't see the animations. Actually, what should happen is that, see, here you have the nucleus and you can take this to be the atom. So this blue one, whatever is there, it comes closer. This blue one, as it is very close to the nucleus, it is the one which is going to deviate more. And then this green one, whatever is there, this green one, it is going to deviate bit less. And if you talk about all these white ones, whatever are there, they are far away from the nucleus, so they barely go deviated. So all these things are going to go undeviated. So what will be the experiment? See, from this we are going to throw alpha particles. We will have a gold foil. Why they have chosen only gold? Because gold is that material, if you can, like, if you try to make it thinner and thinner and thinner, some materials are going to break beyond certain thickness. But gold is something, even if you try to make it as thin as possible also, it won't break, it will hold together and it will look like a sheet only. So gold has that property, that's why he has picked the gold, and he made the gold as thin as possible, and onto that he has sent these alpha particles. So gold is going to have those gold atoms, and whatever the alpha particles are going to go through, majority of the alpha particles have gone undeviated. Reason being, the whole positive charge is more or less concentrated at the center of the atom. So those alpha particles which are going to go close to the center of the atom, they are the ones which have deviated, and the one which is going to go right exactly onto the center is the one which is going to reflect back. So some of them were strongly reflected, some majority of them were not at all deviated, clearly indicating that most of the space of the atom was empty and the whole positive charge is concentrated at a single location, which is going to be the center of that atom. So let us not waste time on that. What are the experimental observations that we got to know from the Rutherford thing? The experimental observations, right? Most of the alpha particles went straight through the gold foil and produced flashes on the screen as if nothing is inside the gold foil. See, flashes in the sense, see, there will be a detecting screen. Every time the alpha particle is going to go and strike the screen, there will be a light coming out, flash. So majority of these alpha particles, they have gone through as if the gold foil is empty. Okay, few particles collided with the atoms of the foil, which have scattered or deflected through the considerable large angles. Few particles even turned back towards the source itself. I said to you, right, those which are going to come directly towards the center, they are the ones which are going to bounce back, and those which are going to be closer, they deviate, and those which are going to be bit far, they go undeviated. That's what all these things are. The entire positive charge and almost the whole mass of the atom is concentrated in small center called a nucleus. Okay, the electrons could not deflected the path of the alpha particles because the electrons are going to be very light. Okay, fine. That strong repulsion thing. Okay, now we need to know something called as impact parameter. So what is that impact parameter? We are throwing alpha particles, right? Yes, the alpha particle is coming far from this gold foil, and take this to be the target nucleus. Take this to be the target nucleus, the gold foil nucleus, whatever is going to be there. Now we send alpha particle. That alpha particle travels. If this was not there, it is supposed to go like this or not? It is supposed to go like this. So the least distance between the undeviated path from the center of the nucleus is going to be called as impact parameter. Now that B is called as impact parameter. Now when the particle goes, once it is going to come closer to the target nucleus, obviously the nucleus is going to be positively charged. As a result, this starts applying force and it is going to be deviating the alpha particle. So finally, let's say the alpha particle goes like this. So it is supposed to go, the alpha particle, if the target material was not there, it is supposed to go like this. But because of this nucleus, now it is going like this. So I can see that the angle or the alpha particle has deviated, and the alpha particle I am taking that it is deviated by some angle theta, and the theta is called as a scattering angle, angle of scattering. So how this b and theta are related? See, we can do a complete derivation, right? You can take the initial momentum, you can take the final momentum, right? You can conserve the angular momentum about the nucleus, you can conserve the energy also, and then the path taken by it is going to be a hyperbola, and then you can use the symmetry. So you can do some calculations, and ultimately the result is important. It is found out that the impact parameter is proportional to cot theta by 2. Impact parameter is proportional to cot theta by 2. On this, there can be questions in JEE mains. It is well within the range of JEE mains. Right? In some of the books, they are going to put it as proportional to under root of 1 plus cos theta by 1 minus cos theta. When you simplify it, you are going to get it to be cot theta by 2 only. Now, if you are going to talk about the number of particles which are going to be getting scattered by one particular angle, so the number of alpha particles which are going to be deviating by or scattered by angle theta is proportional to 1 by sine to the power 4 theta. These are two important things which you people have to keep in mind. So JEE mains might use these two and ask you a numerical question. So the number of alpha particles which deviate or which scatter by an angle theta are going to be related by this. And impact parameter and angle of scattering are related by this. These two results are important. Okay, fine. Take this question. Fine, take this question. See, notification is going to come out soon. Mostly by, you can say, in the month of November, first week or second week, it might come. If they are going to release in the November first week and second week, exam will be bit early, right? The more the time they take, the more it is going to get delayed. The exam shift is going to get delayed. Hi, Nagendra. Okay, fine. Now look. In Rutherford scattering experiment, if the number of alpha particles scattered at an angle of 90 degrees is 55. See, the number of alpha particles that are going to get scattered is going to be, n is going to be proportional to what? Sine to the power 4 theta, man. So then n1 by n2 can be written as what? Sine theta 2 by sine theta 1 to the power 4. To the power 4. Okay. Now n1, how many da? 55. What angle da? 90. So 90 by n2 is going to be, now tell me, they are asking calculate the number of alpha particles scattered at an angle of 60 degrees. So theta 2 is 60. So you will write it as sine 60 divided by sine 90 to the power 4. Then 90 divided by n2 is going to be what? Sine 60 is going to be what? Sine 60 is going to be root 3 by 2. Okay. And what is sine 90? 1 to the power 4. That means you are going to get this to be what? 9 by 16. So 90 by n2 is going to be 9 by 16. Now n2 is going to be what? Automatically 160 or not? Can you clearly see that? As the angle of scattering decreases, we have more particles which are going to have that angle of scattering, because majority of them are less scattered. Very few of them are scattered more. So if the angle of scattering is less, you will have more population which is going to have less angle of scattering. So this is one part which JEE mains hasn't touched till date, but we have it in NCERT. So that's why I have picked up a question, and the impact parameter question also they can ask. They can ask what is the impact parameter when the angle of scattering is 90 and when the angle of scattering is 60. So B1 by B2 will be cot theta 1 by 2 by cot theta 2 by 2. Okay. Yes, Kirti, N1 is... Oh, sorry. You're right, Kirti. My bad. N1 is given as 55. N1 is given as 55. So this is going to be a bad calculation then. So N1 is given 55. Sorry. I'm very sorry. Just got carried away. 55. 55. So you are going to have 16 into 55 divided by n. Sorry, divided by 9. Those many. Okay. Now, what are the failures of the Rutherford's experiment? See, not experiment, Rutherford's theory. He said that most of the space in the atom is empty and the whole positive charge is concentrated at one location, which is going to be the center of the nucleus, center of the atom, and we call it as nucleus. Then what about the electrons? Then Rutherford is like, electrons are going to be revolving around the nucleus in circular orbits. That's what he said. Then everyone are like, they just banged him. They are like, man, you're saying that electrons are going to be what we call revolving around the nucleus in circular orbits. If the electron is in circular orbit, then there is a centripetal acceleration. That means that electron is accelerating. By then, Maxwell has already proved that if there is an accelerated charge, that accelerated charge radiates out energy. Now, people started asking him questions. Maxwell demonstrated already by then that accelerated charges are going to be radiating out energy. Now Rutherford doesn't have an answer. He said electrons are going to move around the nucleus in circular orbits. If it is going to be in circular orbit, there is acceleration. Then the electron should slowly lose energy by radiating out that energy, and it should come and strike the nucleus. When the collisions are made with the nucleus, automatically the atom should be unstable. But the reality is different. The atoms are stable. So he's missing something. When questioned about it, he was not able to explain. So that is one of the major drawbacks of Rutherford. But Bohr is smart. What did Bohr do? He also doesn't know why the electrons are not radiating out energy and why they are not going and striking the nucleus. He doesn't know. So he gave a postulate. What is the meaning of postulates? See, the literal meaning of postulate is that if I am Bohr, I am going to come into a classroom and the class is going to be filled up with scientists. And I am going to be like, I am going to give few postulates. Then everyone has to keep their mouth shut. What is the meaning of a postulate? Meaning of a postulate is you have to accept them without questioning. If you are going to question, then don't listen to my theory, get out of the class. That's what the literal meaning of a postulate is. Without questioning, you just accept those points. If you accept those points, then I have logical answer for rest all. Then I have logical answer for rest all the things. So what are those postulates this fellow has given? Not fellow, due respect to him. With due respect, let's deal with the postulates. So the first postulate is going to be nucleus is heavy, so neglected the movement of nucleus. Neglected the movement of nucleus. Actually, if there is a system where both the masses are going to be moving, generally they will be moving about their center of masses. As the nucleus is going to be so heavy that the center of mass will be more or less at the center of the nucleus itself, because the other one is electron. The other one is electron. So he just neglected the movement of the nucleus. Second, electrons move in stable, which are also going to be called as stationary orbits, as long as electrons exist in those orbits, they don't radiate energy. He doesn't have an answer. He is saying that electrons are going to be moving in circular orbits. Those stationary stable orbits I am talking about, they are circular orbits. He is saying that they are going to be there in the circular orbit, but the problem is, as long as they are there in those particular stable or stationary orbits, electron will not radiate out energy. Now people will question. That's why he has put it as a postulate. Don't question it. If you are going to question, don't listen to my theory. Same problem happened with Rutherford also. Same problem happened with Bohr also. But Bohr is like, I don't know the answer. But if you take it like that, the experimental results are closely matching with the theory. Okay. Okay. Now look. One fine day, he just woke up. He's like, angular momentum is nh by 2 pi. He doesn't know how he got it. But if you use that, you are getting the answers, the conditions are being satisfied, experimental results are closely matching. See, there is a reason why I am saying closely matching. I am going to prove what exactly the experimental results are going to be and how much this fellow has deviated. Okay, so angular momentum of the atom, is going to be, we can write it as m into v into r, which can be written as nh by 2 pi. How he got it? No, he was not able to explain. That's why he has put it as postulate. Okay, fine. These are the three important postulates, man. And then he gave explanation for the transition of electrons also. But one thing which you have to keep in mind is that when he was doing it, he gave it for single electron system once. He gave it for single electron system. So his theory is going to be valid for single electron system. People should not question why only for single electron system. What if the electrons are going to be multiple? Like what if we are going to talk about helium rather than helium plus? So he is like, don't ask me. So whatever he is going to say is going to be valid for single electron system. You can't extend it for multiple electron system because the situation is going to get complicated. Okay. So when I am going to talk about single electron system, we can talk about hydrogen atom, not molecule, hydrogen atom. And we can also talk about hydrogen-like atoms. What are hydrogen-like atoms? Hydrogen-like atoms are those ones which are going to have single electron in them. Example, helium plus, lithium 2 plus, and so on. So we need to always talk about single electron systems. That's what the theory given by Bohr for. Okay. Now, what is the transition rule? See that single electron, whatever is going to be there, it will be moving in circular orbits, right? So mostly it is going to be in the ground state. So now when you give energy to it, it will not take any energy whatever you are going to give. Right? That we are going to talk about in absorption spectrum and emission spectrum thingy. Now the thing is, when the electron, where is this? Ding. Okay, this also has gone. Now, if the PPT, that simulation, all of those things would have been better. Whenever from next time we have a simulation, I'll just use PPT. Fine. We have an electron in an energy level which is some E2. And then there is one more stable orbit whose energy level is, or whose energy value is E1. If the electron is going to go from here to here, when the electron is going to go from this level to this level, it is decreasing its energy. That means it is going to give away some amount of energy in the form of photon. So the loss in energy, whatever will be there, is going to be given out in the form of photon. Generally, higher orbits are the ones which are going to have higher energy. So if you want to talk about loss, it is automatically going to be higher energy minus lower energy is going to be hc by lambda. Now, if we have to talk about the reverse, what is the reverse of it? What is the reverse of it? Now, if we have to talk about, let us say there is an electron here, and for it to go here, then there should be a photon which is going to be striking this, and the energy of that photon should be exactly the same as this energy gap. Now you can write E1 plus that energy of the photon is going to make it go to E2 level. So even now also, what is the energy of the photon that is needed? It is going to be E2 minus E1. It is going to be E2 minus E1. So how much ever energy it takes to go to the next or higher excited states, it takes the same energy to come down, takes in the sense, here it takes, here it gives away. So how much ever energy it has taken here to go up, the same energy it will give away when it is trying to come down. So this is what the Bohr's transition rule is there. Now let us apply the Bohr's theory. What Bohr has said? Bohr has said that electrons are going to be revolving in certain stable orbits. Only in those stable orbits electrons can exist, and even moving in those orbits will not make the electrons lose any energy. Okay. So let us extend to this is the nucleus. This is the nucleus. And now this is different. No. Okay. Let us just go with the circle thingy. Okay. I'll just talk about in general for hydrogen-like. Then what will be the charge of the nucleus, man? The charge of the nucleus is going to be JE. And we have an electron. In which orbit the electron is there? I don't know. So let us take the orbit in which it is there to be some nth orbit. Then the radius of that orbit is going to be what? Rn. And we have electron. And this electron is moving in this orbit, let's say with an orbital speed of Vn. Now, if it is performing circular motion, the common sense is that there should be a centripetal force or not. Now, if you look at the whole thing, what is the only force that is going to be acting between them? The only force that is acting is the force of attraction between this positive charge and the negative charge. How much is that? We can say k q1 q2 by r square. As I have already taken the direction, I don't need to put sign. Now it is going to be k into JE into E divided by Rn square is going to be the force. And that force is the one which is going to provide the centripetal force, right? So Fc is going to be k g e square divided by r n square, and that centripetal force can be written as what? mv square by r. So mvn square by rn is going to be k g e square by rn square. So rn gets cancelled out, so you get mvn square into rn is k e square into g. Now look, there is a reason why I am doing this derivation. Trust me, the way I do it will be very helpful for you. Will be very helpful for you in the times to come. Now you tell me, m into v into r, Bohr's quantization, angular momentum is going to be what? nh by 2 pi. Okay, write that. So nh by 2 pi into Vn is going to be k e square into g. Now, just look, take these things this side. If you take these things this side, what are you going to get? You are going to get the Vn to be 2 pi k. 2 pi is going to go that side. E square g by nh, right? E square g by h n. 2 is a constant, pi is a constant, k is a constant, e square is also a constant, Planck's constant, h is also a constant. So in that case, can I say Vn to be directly proportional to g by n? This is the one which was made to be mucked up by you in chemistry. But this is the actual relation, because rest of the things are constants. Okay, fine, we should not stop over here. This is the velocity of the electron in nth orbit, or speed of the electron, or orbital speed of the electron. You want to call it whatever you want. You can call it whatever you want. Okay. Now, mvn rn is what? nh by 2 pi. Do we know the Vn value now? Yes, we know the Vn value. So, m into Vn is what? 2 pi k e square g by h n is going to be, like, Rn is going to be nh by 2 pi. So, from here, Rn is going to be what? Rn. You just multiplied, you get h square into n square divided by, now look, you have 2 pi and here you have 2 pi, which is going to be 4 pi square m k e square g. Again, can you see h to be a constant? Yes. 4 pi square? Yes. M? Yes. K? Yes. E square? Yes. So the Rn is proportional to what? N square by g. Now look, I didn't get you facts gaming. So photon is light, right? Yes, light is made up of photons. Man, this value, whatever is there, it is 0.529 angstrom. So if you ask me, sir, whether we have to memorize that, not needed. In physics, not needed. and that is also called as Bohr's radius. So Bohr's radius is nothing but the radius of the first orbit of hydrogen atom. If you put G as 1 and if you put N as 1, then you get the radius to be how much? 0.529 angstrom. N is equal to 1 is the first orbit. When you put G as 1, then it is hydrogen atom. So radius of the first orbit of hydrogen atom is going to be also called as Bohr's radius. Okay, fine. Now, we got the Rn, we got the Vn. Now what else we have? I am interested in calculating how much time the electron is going to take to complete one rotation. Time period. Okay, let's go. Time period is going to be obviously what? How much distance it will cover? 2 pi Rn by Vn, right? So for time period, I don't want to get that big expression. I just want to see proportionality. See, time period is proportional to Rn by Vn, and the time period Rn is proportional to n square by G. Vn is proportional to G by n. As a result, the time period is going to be proportional to n cube by G square, right? Now sometimes they are going to be talking about the proportionality of angular velocity. When the electron is moving in the orbit, along with its orbital speed, there will be some angular velocity also. Now obviously that Vn is going to be what? Rn into omega. Vn, the velocity in the nth orbit or the orbital speed, is going to be radius of the orbit into omega. So the angular velocity, if you want to calculate, you don't need to write Vn is equal to Rn into omega. Anyway, we know time period. Time period is what? 2 pi by omega. So time period is inversely proportional to omega. So omega is inversely proportional to time period. So if you talk about time period, you have n cube by G square. So 1 by T will be what? Omega will be proportional to G square by n cube. So like this, you have many things, man. Like this, you have many things. Man, what is the K? Fox Gaming is asking a question, sir, how the K is going to be constant? Man, what's the K value? Coulomb constant, right? What is that? 9 into 10 to the power 9, right? So it's a constant. Okay, fine. We have omega proportional to G square by n cube. Now, some people are going to be like, sir, I want orbital current. I know that, sir, that this will be the nucleus. This will be the nucleus, and I know that the electron is moving in circular orbit. So this electron, as it is moving, it is going to be contributing for some amount of current. So the average current is going to be, in one complete rotation, how much charge will be crossing? E charge. So the orbital current, if I am going to talk about, it is going to be that E divided by the time period. In one complete time period, how much charge has crossed? One electron charge has crossed. Just now we got the time period thingy, n cube by G square. So I can say the orbital current, whatever we are talking about, is proportional to 1 by T. So the orbital current is going to be proportional to what? See, we have T, time period, which is n cube by G square. 1 by T will be what? G square by n cube. G square by n cube. So like that they can ask whatever they want, man. See, now what we realized is that we can treat it as current, right? If the electron is moving like this, then we can take the very same thing as current. We can take the very same thing as current, right? Then current will be moving in which direction? The current is going to be moving in clockwise direction, opposite to the movement. So basically, you can say the orbital current is going to be like this. Orbital current is going to be like this. Now, if they are going to talk about how much magnetic field this is going to create at the center, will you be able to do it? Yes. What is the magnetic field at the center? Mu naught I by 2r. So what is the magnetic field at the center or at the nucleus? Or at the nucleus is going to be mu naught I by 2 times the radius. So I can see that the magnetic field is proportional to I by Rn. We know how I is proportional. It is Z square by N cube. So write that. So the B is proportional to G square by N cube divided by, what about Rn? Is going to be proportional to N square by G. So the magnetic field is proportional to G cube by N to the power 5. So if you ask me a question, sir, should we memorize all of these things? No. I didn't get you. I didn't get you fax gaming. I didn't get you, man, what you are typing. Okay, fine. So is it mandatory for us to go for every possible thing? No. Why I have done all these things then? I'm just trying to show that whatever they are going to ask, you can derive. So the basic things are going to be, you have to remember V is going to be proportional to G by N. You have to memorize that Rn is going to be proportional to N square by G. Now let us go for one important portion that is going to be talking about the energy. That's the most important thingy. Energy is the most important thingy. Okay. Let us talk about the energy that is going to be associated with the electron. With the electron, we know very well that the electron is moving in circular orbit. So as the charge of this one is JE, and as the charge of the particle which is moving is electron, so its charge is going to be minus E. Now they share some potential energy between them, and because of the movement of this electron, there is some kinetic energy also. So what is that kinetic energy? First let us calculate the kinetic energy. So when I talk about the kinetic energy, it is half mvn square. So half m, let us go back. What did we get Vn as? Yes, this is what we have got. Can we copy this? Let me just look at it. Okay, fine. 2 pi k E square G by NH. 2 pi k 2 pi k, what else? E square G by NH. E square G by NH. Man, you have to do squaring on this. So when we do that, you have half small m 4 pi square k square e to the power 4 g square by h square n square. So now I will write the kinetic energy as 2 pi square m k square e to the power 4 by h square into what? G square by n square. This is what you are going to get the kinetic energy as. Keep in mind. Now, I want to talk about potential energy also. When I want to talk about potential energy, when I talk about potential energy, the potential energy is going to be obviously 𝐾𝐞1 𝐞2 by R. So it is going to be K, nucleus is having Ge charge and electron is having minus E charge, divided by Rn. Man, it's going to turn out to be a big thing here. I have to go back in slides. I have to go back in slides. I have to go back in slides and I have to show you this Rn value. I have to get it over there. So which is going to be time consuming. So that's why I'll directly write it. So the potential energy, you people can calculate, but I am directly writing it. You are going to get minus 4 pi square m k square e to the power 4 into g square by h square n square. This is what you will get as the potential energy. Those who have any doubt, you can just go back and see that. You can just go back in the slides, or you would be writing the class notes, right? From that you get the Rn value, put it over there. Now if you look over here, what's happening, man? Kinetic energy and potential energy, if you properly observe it, how are they related? If you look at them, how are they related? Can I say that the potential energy is minus 2 times the kinetic energy or not? Now I want to talk about the total energy. What will be the total energy? The total energy is going to be kinetic energy plus the potential energy, right? And we know that the potential energy is minus 2 times the kinetic energy. So can I simply say that the total energy is minus kinetic energy, or simply half of the potential energy? This is a relation which you would have come across in gravitation also. So not only in these situations, whenever you see an electron revolving in circular orbit, whenever you see not only electron, any mass, for that matter, even if you talk about satellite, what the satellite does around Earth, it will be moving in circular orbit. Whenever something is moving in circular orbit, and if the force is proportional to 1 by r square, if you remember, the satellite is going to experience force due to Earth, and the force of attraction between Earth and the satellite is going to be, like, you can say G m1 m2 by r square. Here also 𝐂𝐤 into minus E by r square, right? So whenever force is inversely proportional to r square, and when you see circular motion, pakka every time you get this. So the total energy, whatever we are talking about right now, is going to be minus 2 pi square. Let us go back. 2 pi square m k square e to the power 4 m k square e to the power 4 by h square into g square by n square. This is the total energy, man. This is the total energy. Okay, now look. Is 2 a constant? Yes. Is pi square a constant? Yes. Is mass of electron a constant? Yes. K? Yes. E constant. H constant. This whole thing is constant, right? So let me just put the value of it. So when I am going to put the value of it, the total energy is minus 13.6 G square by N square electron volt. This is very, very, very important for you to memorize. Very important for you to memorize. And if I am going to talk about if I am going to talk about any hydrogen-like atom, I'm just completing the whole theory, man. Any hydrogen-like atom, if I talk about, if I talk about the first orbit, n is equal to 1, what is the energy of that first orbit? The energy of that first orbit is minus 13.6 g square, because I have put n as 1. Then if I am going to talk about the second one, which is n is equal to 2, so minus 13.6 g square by 2 square, which is going to be this, which will turn out to be how much? Minus 3.4 g square electron volt. And then we have the third orbit, which is going to be how much? Minus 13.6 into g square by 9. I won't do the math. I think as far as I remember, it will come out to be 1.51. Minus 1.51 g square electron volt, and so on. So like that, if I am going to talk about an orbit which is going to be at infinity, which is very far away, then what will be the energy of it? 0 electron volt. Why? Because z square by infinite square you have to do. Infinite square in the denominator is going to be making the whole value of 0. Okay. Now, let us talk about absorption and emission spectrum. So to make you understand absorption and emission spectrum, what I'll do is, I'll just take some sample, some sample of any hydrogen-like atom. On to this sample, first I am talking about absorption spectrum. Onto this sample of hydrogen-like atoms, I throw a spectrum of light. What is a spectrum of light? See, that means I am going to send wavelength of light where all the wavelengths are present. So each vertical line belongs to wavelength. And I am going to throw a spectrum of light. That means I am throwing onto this hydrogen-like atom all those wavelengths, continuous wavelengths I am going to throw. Each vertical line belongs to certain wavelength. Wavelength of what, man? See, when you throw light, what actually you throw? You throw photons. So you can say each vertical line belongs to one photon. See, don't spam the chat. Nalagondla Radha, you're saying when will you teach fluids, right? See, fluids will come. I think in this row series, sir would have already done, right? Okay. Now, each line belongs to certain wavelength, right? Okay. Now we are throwing all those photons into this hydrogen sample. Then what was observed is that only those photons were observed which can make the electron go to next higher energy levels. Only those photons were absorbed by electron which is making it to exactly reach higher excited states. Sir, give me one example. Give me one example. So I'll take hydrogen atom only. If I am going to talk about hydrogen atom, what is the ground state energy? Minus 13.6 electron volt. Right? What is the next one? Minus 3.4. And what is the next one? Minus 1.51. Something. So, if you look at the energy gap over here, the energy gap over here is 10.2 electron volt. The energy gap over here is how much? 12.09. So, if we talk about electron being in this state, then if it gets 10.2 electron volt of photon, it takes it and goes here. If it gets 12.09 electron 1, then it is going to go directly to n is equal to 3. So from n is equal to 1, it will go to n is equal to 3. If this electron is given 10.5, no, it won't take it. Why? If it is going to be taking 10.5, it can't reach this state, or it can't exactly reach this state. So that energy, whatever is given, electron won't accept it. Why? Electron is not allowed to exist in any other state apart from these states, as said by the Bohr's theory. Only certain orbits are stable, and in those orbits only electrons can't radiate out energy. So the electrons will exist only in those stable orbits. So these are those orbits. So if the photon, whatever is going to be given to the electron, if it is capable of making it exactly reach the next higher excited state or the next one, then it takes it and it goes. Otherwise it doesn't. Okay. Next. Sir, will this photon be also absorbed? There is some energy gap between these two also, na? Which is how much? Some 1.89. Yes, 1.89. 89, yes, 89. So will that also be absorbed? Yes, sir. Arey, sir, I didn't get you. There is only one electron. Man, I have taken sample of atoms. Hydrogen-like atoms I have taken many. So there will be one such atom where electron has taken 10.2 and it has gone over here. So when it is here, there is one more photon of 1.89 electron volts is going to strike it. Then it is going to go to n is equal to 3 also. Because I am not talking about one single atom. I am talking about a sample. So there are many atoms and many electrons, and photons can strike all those things. So what are all those photons which will be missing in this spectrum? The energy gaps, whatever are there, those photons are going to be missing. Now you should get one doubt. Sir, if the energy is going to be more than 13.6, then what will happen? Yes, then it can take it. Why? I'll explain. So the electron which is going to be over here, its energy is minus 13.6. So if this is given plus 13.6 electron volt, then the total energy of that electron will be what? 0. That means it escapes. So no longer it is bound to the nucleus, or no longer it will be there in the atom. If it is there in the atom, then the atom is asking the electron to be only in particular orbits. If it is free from the atom, it can stay wherever it wants, man. So if the energy of the photon that you are going to supply is going to be greater than or equal to 13.6 electron volt, the electron can take those photons and atom gets ionized. Atom gets ionized. Electron is leaving, right? So there will be something called as ionization energy. What is ionization energy? Ionization is the minimum energy that you have to give to the electron such that it gets free. So what is the ionization energy in the case of hydrogen atom? 13.6. Fax gaming, can you recharge me? Come on, man. Watch tomorrow. Watch tomorrow. Okay, fine. So what is ionization energy? If you give an energy which is going to be making it free, then all those photons can be taken. Sir, why did you use the word can be taken? Why didn't you use the word will be taken? That's the problem with electron, man. Electron, when it is given energy, it might take it or it might not take it. So basically, if 13.6 electron volt photon is going to be given to this one, then also it might take it or it might not take it. Is it allowed to take? Yes, the atom allows the electron to take. 13.6 amount of energy, atom allows electron to take. But still then, whether electron will take it or not, it depends on it. So every time when you give an energy of 13.6, don't think that electron will definitely take it. So if they are testing your conceptual clarity, this won't be there in the books. This is one common misconception. This is one common misconception. People think that if the electron is given 13.6, definitely it will take it. No, it is allowed to be taken, but it will take or it will not take. It's up to the electron. One more example I'll give you. For example, if this electron is given 10.2, so 10.2 makes this electron exactly go to this state. So will it take means, first of all, is it allowed to take? So allowed to take means atom should give the permission. Yes, if the photon is having 10.2 energy, then atom says that electron, you can take it. But then whether the electron will take it or not, it depends on it. So please be careful. If they say that electron must take, then it is wrong. Even though the photons which are allowed to be taken by the electron, allowed by whom? Allowed by the atom. Even though the energies which are allowed to be taken by the atom, whether the electron will take it or not, it depends on its mood. You can think in that way. Okay, enough. That is one extra point which you don't find in the books. Okay, fine. Now, what is this emission spectrum? What is that emission spectrum? What is that emission spectrum? Now, before we go for that, I said to you, right, there will be a band. How they experimentally found out that some of the photons have been observed and what are the exact photons which are observed. See, whatever the photons are taken by the sample of atoms, those vertical lines will be missing because those photons are missing. You throw light and you detect the light what you have got. You throw light onto the sample and whatever the light that has come out of the sample, we trap it, and when we count, some of these vertical lines will be missing, clearly indicating that some photons have been absorbed. So when you look at the photons which are absorbed, only those photons which are making the electron reach exactly the next higher excited states are absorbed. That's it. That's how they found it. Okay, next. Now, what is this emission spectrum? You throw light, right? And you are going to be detecting the light which has come out. Now, some of the photons have been absorbed by this sample of hydrogen-like atoms, right? So, by absorbing those photons, electrons have reached higher excited states or not? Now they'll try to come back, man. Because they don't love to stay there, because they are more stable when their total energy is lowest. You know this thing, everybody or everything wants to be at its lowest energy. So energy is lowest where is the energy lowest? And the ground state. Anyway, we are talking about one electron, so definitely ultimately the electron wants to go back to its ground state. So for example, let us take that the electron I am talking about is here in the fourth state. Now there are possibilities to it. It can directly jump from 4 to 1, that is one possibility, or it can jump here and then to here, or it can jump here then to here, or after jumping here it can jump here and then to here. So in all these possibilities, if you are going to look at this one and this transition, gives you same photon, and if you are going to talk about this one and this one, both of them give the same photon, so they won't be counted as two different lines in the spectrum because they belong to the same wavelength. So one line only you are going to draw. These two also you are going to draw only one line. Next, is there any other common thing? No. Now you tell me how many spectral lines will be absorbed, will be observed. You have this spectrum drawn like this photon, this photon, this. So 1, 2, 3, 4, 5 and 6. So total you are going to have 6 different photons coming out, and those 6 different photons will have 6 different wavelengths, and all those 6 wavelengths, 1, 2, 3, 4, 5, 6, these 6 wavelengths will be present in that spectrum. So this is going to be called as emission spectrum. Now you should generally get it out. Sir, we have only one electron. When we have one electron, then this electron can jump from here to here. That's it. Or it will jump from here to here and then to here to here. But how are you counting multiple possibilities? But when we have a single electron, how are we calculating multiple when we have a single electron? Man, think. I am not talking about single electron system. I have many hydrogen-like atoms. So I have many single electron atoms present. We have a big sample. We have a big sample. So in that big sample, there will be many atoms having electron in the fourth state or third excited state. So in one atom, there will be this transition. In some other atom, there will be this transition. In some other atom, there will be this transition. In some other atom, there will be this transition. So don't think that this single electron only is doing all these transitions. No. If you use your common sense, if this is a single electron, then it can directly jump from here to here. Only one photon is going to be coming out. Or it can go from here to here, here to here, here to here. Then 3 photons. Maximum, if it is a single electron, 3 photons can be emitted. But we are not talking about a single hydrogen-like atom. We are talking about sample of atoms. So in that sample of atoms, we will have many electrons which are going to be in n is equal to 4. So some electrons go like this, some electrons go like this, some electrons go like this, some electrons go like this. As a whole, we get 6 spectral lines. That's why they will ask the number of spectral lines. rather than asking the number of photons. Why? See, if they are going to count the photons, na, here we counted this as one line because they will be having same wavelength. But how many photons are there? Two photons are there. Here, how many photons are there? Two photons are there. But for those two photons, na, when you draw the wavelength in the spectrum, you'll get only one line. So that's why they will always count spectral lines rather than the number of photons. Number of photons will be more than the number of spectral lines. Okay. Sir, here we are able to calculate it easily. Is there any shortcut where I can calculate the total number of spectral lines? Yes. Yes, we can. The shortcut is going to be, for example, we are talking about N2 level and it is coming to some N1 level. The electron ultimately from N2 level is coming to the N1 level. Is coming to the N1 level. Okay, fine. What is the shortcut? So the number of spectral lines can be written as sum of N2 minus N1. So how do we need to? Let us just give me an example. Let us take the example of the last case itself. What is the last case? N is equal to 4 to N is equal to 1. Okay. So N2 is what? 4. N1 is 1. So we have to sum 3, right? So how is that sum 3? From 3, the next number 2 and the next number 1. So this is how you should expand this sigma N2 minus N1. So if they are going to talk about, for example, starting from 5 and going through or going to 3, then it is going to be sigma 2. How you should expand it? 2 plus 1, which is going to be how much? 3. I'll give you one more example. That example is, let's say it is transition from 10 to, let us say, 5. Then it is going to be sigma 5. Then 5 plus 4 plus 3 plus 2 plus 1. These many spectral lines are possible. And keep in mind, sample of atoms is different, single atom is different. Sample of atoms is different, single atom is different. If they talk about single atom, and if they talk about maximum number of spectral lines, let us take this situation only. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, and we have this electron here. Now we have only one electron. If it is going to directly jump here, then only one line will come. One photon will be emitted. But I am talking about what can be the maximum spectral lines possible. So if you want maximum spectral lines, maximum transition should happen. So first it should go from here to here. So one photon will be emitted. Then it should go from here to here. Again one photon will be emitted. And then from here to here, again one photon will be emitted. So in this case, the maximum number of spectral lines possible are 3. So that's why I am telling you, be careful whether they are talking about single atom or they are talking about sample of atoms. If it is lower level examinations, you don't worry whether they mention it or not. Generally they take sample of atoms. But if it is JEE advanced or any higher level examination, you have to be very careful. So if it is a single one, then 3 lines, maximum 3 lines are possible. If it is a single line, maximum 3 lines, single electron, maximum 3 lines are possible. If it is sample, yes, then these many. How many? These many. Never ever forget, I'm highlighting this. This formula is valid for sample of atoms. Not single atom, many atoms. Many atoms. Okay, fine. What is very famous? The famous thing is hydrogen spectrum, man. Hydrogen like atoms spectrum is not famous. Hydrogen spectrum is very famous. Thank you, Santosh. Santosh is saying that good teaching. Thank you, man. Why after every half an hour or 40 minutes I am replying is that people should not think that it is a recording. Right? I know very well those who are seriously preparing, for them even 1-2 minutes of casual discussion is going to be waste of time. Their flow gets broken. So honoring those people's request, right, I'm doing majority of teaching continuous talking, right? As a result, some people think that it is a premiere. No, man. If you comment, if it is something worthy, I'll definitely look at it and then I'm going to reply to it. Okay. Hydrogen spectrum. First of all, what is the energy of the first orbit? Minus 13.6. Next one, minus 3.4. Next one, minus 1.51. The next one, minus 0.81. And one more thing, man. You better keep this also in mind. The energy gaps. The energy gap here is actually 12.09. But if you get a question where the energy of the photon is coming out to be 12.1, still you just take it. Actually, the gap between these two, if you talk about, it is how much? The 12.1, no, 12.09, right? So if I am the one who is framing the paper, then definitely I'll make sure that the energy of the photon is going to be 12.09. But in some situations, they just neglect that, right? If you get a photon whose energy is going to be 12.1, still you take that it is going to go from n is equal to 1 to n is equal to 3. Okay, what are important? As I said, I would request this and this to be memorized by you, not rest all. And I have seen situations where this was also a bit helpful. I have seen situations where, like, I have seen questions where this is also going to be helpful. So these three you have to memorize. This is what to go from 1 to 2. This is what to go from 1 to 3. And this is what to go from 2 to 3. Keep in mind. So to go from 1 to 2, this much is needed. If it is coming from 2 to 1, then this much will be emitted. Okay, fine. Now, we have energy of the levels to be what? Minus 13.6 g square by n square. So E1 is going to be what? Minus 13.6 g square by n1 square. E2 is going to be what? Minus 13.6 g square by n2 square. And for your kind information, you can put g as 1. We are talking about hydrogen, but I don't want to put g as 1 as of now. Okay. Now, what was the transition rule given by Bohr? The transition rule given by Bohr was the energy of the photon that is going to be coming out when from higher level it is going to fall to the lower level is the difference of the energy, right? So then you will be having what? Minus 13.6 g square by n2 square minus of minus 13.6 g square by n1 square. So as a result, you get 13.6 into 1 by n1 square minus 1 by n2 square into g square is energy of the photon. Energy of the photon is going to be what? hc by lambda. So 1 by lambda is going to be what? 13.6 electron volt by hc into 1 by n1 square minus 1 by n2 square into g square. For your kind information, 13.6 electron volt is a constant, h Planck's constant, c constant. So this is represented with something called as Rydberg's constant, Now that's very famous for you in chemistry, but to be honest, I won't use this. I won't use this. Do you know why? Man, I'll use this one. Whenever I am in need of calculating the wavelength, I'll use that. How? Already we have learned that energy of the photon in terms of electron volt can be written as what? Roughly 12,400 electron volt angstrom by the wavelength is going to be 13.6 electron volt into 1 by n1 square by n2 square into G square. So I'll use this rather than using this. Chemistry people love to use this, but I personally prefer this one. I personally prefer this one. Now look, whenever the de-excitation is going to be happening to n is equal to 1, whenever the de-excitation is going to take place to n is equal to 1, then whatever the photon is going to be emitted, that photon will have some wavelength, and in the spectrum that wavelength will belong to one particular line. So like that, when the de-excitation is happening to n is equal to 1, it can happen from 2 to 1. If it is happening from 2 to 1, then you will get one wavelength photon. That wavelength will belong to one line. 3 to 1, one photon, that will have one wavelength, one line in the spectrum. 4 to 1, one more line. Like that you will get many lines, right? All those lines put together are going to be called as Lyman series. That's it. All the vertical lines in the spectrum, when the de-excitation happens to n is equal to 1, all those lines put together are called as Lyman series. So even the namings, they are damn good, man. Like it's not random thing. It's not random. So what is that? De-excite. Didn't detect. Okay. When the de-excitation is going to be to n is equal to 1, all the photons whichever have come out, we'll call them to be belonging to Lyman series. We'll call them to be belonging to Lyman series. Now look, man. So we realize that it should fall to n is equal to 1. Should fall to n is equal to 1. Then it can fall from n is equal to 2. It can fall from n is equal to 3. Or it can fall from n is equal to infinity also. So I want to talk about the maximum wavelength of the photon that can come in Lyman series and the minimum wavelength of the photon that can come in Lyman series. Maximum wavelength and the minimum wavelength that can come. Right? Okay, fine. Look, energy of the photon is going to be hc by lambda. For lambda to be maximum, energy of the photon should be minimum. Agreed? And for lambda to be minimum wavelength of photon, then the energy of the photon should be what? Maximum. And if I am going to talk about maximum energy, the energy of photon depends on what? Energy gap. So when the energy gap is maximum, if the transition is from infinity to 1, energy of the photon is maximum for which transition? For which transition? For a transition which is from infinity to 1. For a transition which is from infinity to 1. Okay. Now, what is the energy of the infinity, sir? Energy of the infinity is 0. What is the energy of the first one? Minus 13.6. So what is the energy of the photon you are going to get? Difference of the energy, which is the energy of the photon you get is 13.6 electron volt. So I can write it 12,000 electron volt angstrom divided by the wavelength is 13.6. So look man, here I have taken the approximate value. So the wavelengths we get also are going to be approximate. The wavelengths we get are also going to be approximate. So 12,400 divided by 13.6, you get roughly the wavelength to be 911 angstrom. This is less than the visible. This is less than the visible. So now I clearly realize that Lyman series is not going to be in the visible region. It is even stronger. Wavelength less means it is going to have more energy. Okay, that means it should belong to UV. Should belong to UV. So let me just talk about the maximum wavelength also. Then I can completely decide the region in which it lies. So if I am going to talk about the photon's minimum energy, so minimum energy means minimum energy gap. You tell me here this much energy gap. If you go for 3 to 1, this much. 4 to 1, this much. So the energy gap is increasing if you go for higher orbits. So least energy gap is between 2 and 1 because 1 is fixed. So the least energy gap is between 2 and 1, not 3 and 1, not 4 and 1. So the transition should be from 2 to 1. Then the energy of the photon that is going to be coming out will have how much energy? 10.2 electron volt. 10.2 electron volt. And roughly we can say 12,400 electron volt angstrom divided by the wavelength, which is 10.2 electron volt. So the wavelength, the maximum wavelength you can get, I'm being honest, I'm using calculator. 12,400 divided by 10.2 roughly comes out to be 1215 angstrom. So the whole region of it is falling in what? See, the least wavelength you can get in Lyman series is 911. And the maximum wavelength you can get is this much. And if you talk about the whole range of the wavelengths or the wavelengths of all the photons that are going to come when the de-excitation happens to n is equal to 1, all those photons have wavelengths ranging between 911 to 1215, and wavelength 911 to 1215 is UV region. So Lyman series emits photons in UV region. Okay. What is the next series? Lyman and Balmer are important for competitive examinations. Rest of them are not that important. So that's why I will also focus more on these things. Right? Don't mug up anything. In examination, you can find. Even you see, being a teacher, after I have taught roughly what? 9 years, 10 years? More than 9, close to 10. After all these 10 years of experience, you see, when I am talking about these things, did I mug them up? In front of you, right in front of you, I have used the calculator and I got those values. So you also don't need to memorize, man. Okay, fine. When we call Balmer series, when the de-excitation is going to be towards n is equal to 2. So that means, let me show you, we have electrons in the higher orbits. If they de-excite to n is equal to 2, whatever the photon will come out, that photon will have wavelength, and that wavelength will be one vertical line in the spectrum. So all those wavelengths, all those vertical lines in the spectrum put together are called as Balmer series. So what is Balmer series? When the de-excitation happens to n is equal to 2. When the de-excitation happens to n is equal to 2. Okay, let's do that. Now n is equal to infinity, n is equal to 2, this is n is equal to 1, and what is the energy gap here, sir? As far as I remember, the energy gap here was 1.89 electron volt. And what is the energy of the second orbit? Minus 3.4 electron volt. So n is equal to 3, n is equal to 3 to n is equal to 2. We have that. Okay, fine. Now same story. If you want maximum energy photon, maximum energy gap for n is equal to 2 is there with n is equal to infinity. So if you want a photon of max energy, then the transition should be from infinity to 2, right? So then the energy of the photon we talk about is going to be 3.4 electron volt, because the energy at infinity is 0. If the electron is coming to minus 3.4, it has lost 3.4. That whatever the energy it lost, it will give away in the form of photon. Okay, fine. It's 12,400 eV angstrom divided by lambda is 3.4 eV. So what's the lambda, man? Let's see that. 12,400 divided by 3.4. So I get the lambda to be around 3647 angstrom. Now let us talk about the minimum energy photon that can come out. Minimum energy means minimum energy gap. From n is equal to 2, the minimum energy gap is there for n is equal to 3. So if I am going to talk about this photon, if I want the photon of minimum energy in Balmer series, then we are referring to the transition of 3 to 2. Then the energy of that photon is going to be in how much? 1.89 eV. So then 12,400 eV angstrom divided by the wavelength is going to be 1.89. So the wavelength that you are going to get is 12,400 divided by 1.89, which will be 6560 angstrom. Isn't it in the visible region? I think 3,500 angstrom to around 7,000 angstrom is going to be visible region, right? So the Balmer is going to be giving out photons which are going to be in the visible region. So Lyman series is UV, and UV is a bit dangerous, and Balmer series, yes, we are going to get visible light. What about the other three? So after visible we will be having infrared. So in the case of the other three, I won't even write them, which is waste of time. So if I am going to talk about Paschen, bracket and P fund, they haven't even written that P fund thingy. Paschen, bracket and P fund are going to be in infrared region. So I am not writing that. If you want, you can just add it over here. Yesterday I tried adding a page and it got screwed, the whole thing. Okay, so I'll write it here. I don't want to risk it. So other three series 1 will be in infrared region. Other three series one will produce photons which will be having wavelengths falling in the infrared region. So lambda is greater when the transition from n plus 1 to n. Obviously man, because if you are talking about transition to n, the next immediate one is the one which is going to be closest, so the energy gap will be less. So if the energy gap will be less, then the photon energy will be less. Obviously wavelength should be more. I explained it, yes. Energy of photon is hc by lambda. If you want least energy, then wavelength will be maximum. If you want least energy photon is going to be coming when there is transition from two successive energy levels. Yes, Mr. Fajr. Okay. Oh, lot of theory, man. Continuously I was talking. I gave the whole theory. Now majority of them are questions. We have some JEE mains questions and we also have some JEE advanced questions taken in this class. Because my aim was to make you reach up to advanced level at least for the easier chapters. According to me, modern physics is easier, and even the students every year give a feedback that the chapters are easier. Right? So do this. I remember something was wrong with this. Let me see whether we will get the answer or not. This should be minus 4 e by 3. Minus 4 e by 3. Okay. Did I give one more page to this? No. So I have to fit in over here itself. So we have transition, man. One transition from here to here, and that transition is lambda 2. They are talking about ratio. Lambda 1 by lambda 2. So what is the energy of this blue photon? So the energy from minus E, it is going to minus 4e by 3. So minus E, and the energy gap between them is E by 3. That E by 3 comes out in the form of photon, which is hc by lambda 2. I'll write it as equation 1. Now I'll use a different color. I'm using green for this transition. For this transition, what is the energy lost? You can clearly see that the energy lost is going to be E. So that E is going to be equal to what? hc by lambda 1. hc by lambda 1. Now what are they talking about? They are talking about ratio of lambda 1 to lambda 2. That means equation 1 divided by equation 2. So when I do equation 1 divided by equation 2, then E by 3 and E on the left side, E gets cancelled out. You get 1 by 3 to be equal to lambda 1 by lambda 2. So lambda 1 by lambda 2 should be equal to 1 by 3. So your answer is option 3. Come on, man, you have to answer. You have to answer. We Enthuse Club, good evening, everyone, good evening. See, why I replied now is that don't think that it's a premiere, and don't think that it is a fake live also. I see the comments. Come on. JEE Mains 2019. I have picked questions of JEE Advanced also. In a hydrogen-like atom, when an electron jumps from the M shell to the L shell, see, they haven't given information in the form of n is equal to 1, n is equal to 2, but they gave it in form of ML. You know the naming, right? KLM. So K shell is going to be n is equal to 1, L shell is going to be n is equal to 2, right? So M shell is going to be, as I said, K, L, M, N, O, like that. The naming is like that. So K means n is equal to 1. K, L means n is equal to 2. M, n is equal to 3. And so on, right? So basically M to L shell is nothing but 3 to 2 transition. Right? Now what they are asking, Wavelength is lambda, it seems. If an electron jumps from N shell to L shell, the wavelength of the emitted radiation will be, sir, 1 by lambda is Rydberg's constant into 1 by 4 minus 1 by 9. This is our first thing. Now they are talking N to L. That means 4 to 2. They are asking that wavelength. So I'll write it as 1 by lambda dash is R into 1 by, what you'll have, 4 minus 1 by 16. So let us simplify this. 1 by lambda is going to be R into 5 by 36 is what you get here. And 1 by lambda dash is going to be R into, it is going to be 3 by 16. So now you can relate them. I am leaving this calculation part to you. It's not a big deal. Okay. Do this one, JEE Mains 2019 online. See why I am picking JEE Mains questions which are of 2018, 2019 and I'll pick 2020 also. Because that's the pre-COVID thingy. And JEE Mains, like the NTA has recently said that it is going to go back to pre-COVID. So I'm thinking that the level also will go back to the pre-COVID. So if we can do 18, 19, 17, those questions, right, it will be better. A helium plus ion in its first excited state. First excited state means N is equal to 2. Ground state is N is equal to 1. First excited state is N is equal to 2. Its ionization energy is, man, ionization energy means what? You are talking about the energy which makes it free. So it is in first excited state, N is equal to 2. What is the energy of N is equal to 2? It is minus 13.6 into Z square, G square by N square. Helium, G is 2. So G square by N square. So helium, the second orbit has this much energy. So if the electron is here, the total energy of that electron is minus 13.6. So if we give plus 13.6, it becomes free. So the minimum energy which we have to give to make it free is ionization energy. So how much we have to give, sir? 13.6. Option 2. Come on, come on. You people have to respond. You have to respond. There are people watching live. You have to respond. All the hard work I have done till now is presented over here. Questions. Come on. Consider a hydrogen atom with its electron in the nth orbital. Okay. An electromagnetic radiation of 90 nanometer is used to ionize the atom. If the kinetic energy of the ejected electron is 10.4 electron volt, then the value of N is, they asked to take Hc as 1242. So if I am going to take the energy to be Hc by lambda, that Hc was asked to be taken 1242 electron volt nanometer. And what is the wavelength they have thrown, man? The wavelength they have thrown is 90 nanometer. Let's kick it out. See, I have the liberty of using calculator. I'll use that. 1242 divided by 90, which will come out to be 13.8 electron volt. So the photon we are talking about is giving this much energy. So the energy is given to the photon. So this energy is given, this energy is given to the electron. When energy is given to the electron, some energy it takes to come out, which is nothing but the ionization energy, plus rest will be in the form of kinetic energy, right? Rest will be in the form of kinetic energy. How much energy you provided? You provided 13.8, sir. How much energy it is going to take to come out, that I don't know. But I know how much kinetic energy it has. It has 10.4 electron volt. So 13.8 minus 10.4 is going to give that the energy it needs to come out. The energy it needs to come out is 3.4 eV. It's going to be 3.4 eV. Man, that means we know that this is minus 13.6, n is equal to 1, n is equal to 2 has minus 3.4. So if the electron is in this state, it needs 3.4 to get free. So if you give 13.8 to it, then 3.4 it uses to free itself, and rest it will store in the form of kinetic energy. So we are talking about electron in which state? N is equal to 2. N is equal to 2. JEE Advanced 2015. Is it difficult? Nah, it's not difficult. Right? Voice is not clear. What about other people? Can you comment on the voice? Please do comment immediately. Is the voice clear? Meanwhile, others do this question. Please comment. Those who are live, please comment. Vontela, Vikshita, is it clear now? Is it clear now? Vikshita, is it clear now? Hey, I'm waiting for you people to reply, man. I'm waiting for you people to reply. Come on. Okay. Now I think it's clear. Okay. An electron in an excited state of lithium 2 plus ion has angular momentum. Man, the moment they give angular momentum 3h by 2 pi, na? The moment they are going to give the angular momentum as 3h by 2 pi, compare it with, it is nh by 2 pi. So the electron is in second excited state, or in n is equal to 3. The de Broglie wavelength of electron in this state is p pi a naught, where a naught is the Bohr's radius. Man, look, if we talk about the radius, you can write it as Bohr's radius into n square by g. Always keep that in mind. Now they are talking about de Broglie wavelength. So how do we get the de Broglie wavelength? Where is this? Okay. So lambda is going to be what? H by m into v. Right? Now that can be written as h by root 2m ke. We have a relation. The total energy and all those things we can calculate, right? See, if I am going to talk about the kinetic energy, it is going to be minus of half of the potential energy. So from all those things, can we calculate? Either we can go like this. Now, don't you feel that this is turning out to be slightly lengthy? But definitely we are going to get the answer. We will get the answer. But don't you feel that writing kinetic energy and then potential energy, K, Q1, Q2 by R, man, ages da, ages. But one second, just a second. If we look at only this section, we know angular momentum is m into v into r. And if I'm talking about m into v is going to be angular momentum by r. We are done. We'll easily get it. We will easily get it in this way. Angular momentum is given as 3h by 2 pi, put 3h by 2 pi. And then you know the n value, you know the g value. G is going to be 3, n is going to be 3. You put them, you get the answer. It's JEE Advanced 2015. Those who are going to think of writing MV as like this and then trying to get like this, for them it will turn out to be lengthy. But keep in mind, you can use MVR is equal to NH by 2 pi. So when you see that the calculation is turning out to be lengthy, especially in atomic physics, not only atomic physics, even in modern physics, there might be one more way. Just keep that in your mind. Sir, why do you look like that, sir? It's scary. Man, I love physics so much that when I keep explaining, I just go into the world of physics. I forget how my expressions are. I involve so seriously that my face looks serious. What to do? Manufacturing defect, man. Manufacturing defect, macha. I love physics so much. I get it happens. What to do? It happens, man. Okay, come on. One more JEE advanced question. One more JEE advanced question. A hydrogen atom in its ground state is irradiated by a light of wavelength 970. Okay. They asked us to take HC value also to be 1.237 into 10 to the power minus 6, and the ground state energy level of hydrogen atom as minus 13.6. The number of lines present in the emission spectrum. First of all, we have to see how much energy you are supplying. Na? So what is the energy of that photon that is being supplied? The energy of the photon is 12370 into, I'm converting it, I'm directly converting and doing it. Electron volt, angstrom, whatever they have given, divided by the wavelength. They have given 970. So 12370 by 97. 1237 divided by 97 gives 12.75 electron volt. So for minus 13.6, if you are going to give 12.75, what is that you are going to get? Minus 13.6, 12.75. My brain got saturated, that's why I'm using calculator. You get this, right? Where do you get this energy? See, n is equal to 1 minus 13.6. N is equal to 2 minus 3.4. N is equal to 3 minus 1.5. N is equal to 4. For n is equal to 4, you get minus 13.6 by 16. So minus 13.6 by 16 will be how much? 13.6 divided by 16 is what? 0.85 minus 0.85. That means that particular electron will go to n is equal to 4. Right? Now they are talking about emission spectrum. That means generally they are going to talk about a sample, I said to you, right? A sample. So n is equal to 4 2, n is equal to 1. So sigma 4 minus 1, which is going to be 3 plus 2 plus 1, which is going to be 6. Hey, it's okay, man. Ritvik. See, everyone have their right to share their opinion. But look, you might have a doubt. See, sir, they said hydrogen atom. That means they would have said single hydrogen atom. Man, it is JEE advanced. Those people are damn good. Even with the English also, they said a hydrogen atom. And they are talking about emission spectrum. Emission spectrum is going to be taken for a sample of hydrogen atoms, right? Keep that in mind. Just be careful. Next, this question, will you take it as homework? Hey, like I have done a lot on these things. Can you take it as homework? This question, this is also a JEE advanced question. I think as far as I remember, it is 2024. JEE advanced 2024. Only this option is going to be tricky. Only this option is going to be tricky. See, look, they mentioned that m is an integer. Just check whether always you get integer square or not. Whether always you will get integer square or not, you check. Otherwise, then mark this option as wrong. So the only tricky option over here is this. Only tricky option over here is this. Okay. Do this one. You can see the heading here. Extension of Bohr's model to other systems. See, they are going to simply explain something and say that assume Bohr's quantization is valid here. So they won't talk about electron revolving around the nucleus. They'll talk about some random system and they say that assume Bohr's quantization is valid here. Man, bad. Assuming Bohr's quantization valid here is a bad thing. Bad thing in the sense, not too difficult, but we have to do the whole calculations again. Whatever we have done for the electron atom, do you remember 𝐂𝐞 and 𝐞2 by r square? And from there we got the radius, then from there we got the velocity, and from there we got the total energy. So when they extend the Bohr's model to some other situation, you have to do the whole calculations again. That's why. Okay, a particle of mass small m moves in a circular orbit where the central potential, they gave potential, they didn't give force. The potential field they have given is that if the Bohr's quantization conditions are applied, the radii possible orbitals and energy levels vary with the quantum number n. As in the options, they are talking about r and they are talking about energy, both. You have potential energy field. So the potential energy is given as k r square by 2, sir. How to get force from that, sir? Force from that is minus du by dr, sir. Long ago in work power energy, you people would have come across that. So I get the force to be this, sir. The minus indicates that it's a force acting towards center, sir. So that's the force which will provide centripetal force, obviously, because we are talking about a particle of mass small m moving in circular orbit. So there should be someone who is going to be providing centripetal force. Yes, this is that which is providing centripetal force. We have it, and we have that mass, and that mass is going to be experiencing a force which is going to be dragging it towards the center. And if I take the radius to be smaller, that force is kr. Sir, why didn't you put the minus sign? I have already given the direction. That force is opposite to r bar. This is your r bar, force will be opposite to it. That's the one which is providing centripetal force. So I can say mv square by r is this. Now the mv square is kr square. So I can say r is proportional to v. But we don't want it in that way. Okay, let us erase this. Now I need r in terms of n. I need r in terms of n. Okay, I have mvr is equal to nh by 2 pi. Then m square v square r square is n square h square by 4 pi square. I'm singing. Man. M is a constant, h square is a constant, 4 is a constant, pi square is a constant. So I can say v square is proportional to n square by r square. So from here, that v square, you can write it as what? N square by r square. So n square proportional to r to the power 4. So r proportional to n to the power 1 by 2. Which option, sir? N proportional to r to the power 1 by 2. Which option? Yes, we have 2 and we have 4. We have 2 and we have 4. Now if you look at the energy, sir, energy is proportional to r square and r is proportional to n to the power 1 by 2. So the energy is proportional to r square. Then it's proportional to what? N. So which option? R proportional to root n, energy proportional to n. So option 4. These questions are a bit frequent in JEE mains. When the paper is going to be difficult, yes, they ask these questions. Very good, Ritvik. Ritvik Krishna, very good. Very good, Ritvik Krishna. Just to prove that it's alive. And it's an encouragement for Ritvik also. Well done, man. If one were to apply Bohr's model to a particle of mass small m and charge q in a plane under the influence of magnetic field B. One of the worst questions I have come across. Why? Man, they didn't say how it is moving. Da. They should say that it is moving in circular orbit. Na? What if it is going to be moving like a helical path, or what if it is going to be doing something else? So if one were to apply, so I am assuming that moving in a plane under the influence of magnetic field, okay, obviously they said moving in a plane. If it is a helical path, the plane has to change. Okay, good, my bad. If it is going to be movement in the plane, then it has to be circular motion. And if we have a charged particle moving in circular path, having some V, radius R, and some magnetic field B, yes, there is a force QVB is going to be acting towards the center, right? And that's the one which is going to be providing the centripetal force. So the FC is going to be QVB. What they are asking you to find? The energy. To get the energy, see here, there is no potential energy. It will have only kinetic energy. That means we need V. Okay. mv square by r is going to be QVB. So from here, what will be the V value? V is going to be RBQ by M. And then we have MBR is equal to NH by 2 pi from Bohr's model. Right? So let us do one thing. Because we need V. So let's eliminate R. So from here R is going to be what? MV by BQ. So let us go and put it over here such that everything will be in terms of V only. So then M into V into R is going to be what? mv by bq is going to be nh by 2 pi. So from here you have, I'll keep mv square this side, rest I'll take to that side, is going to be nhbq by 2 pi m. 1 m I'll take this side. Now I need kinetic energy. That means I need to multiply half on both the sides. So if I multiply half on both the sides, yes, I get the kinetic energy, which is nothing but the total energy. So I should have nhbq by 4 pi m. nhbq by 4 pi m. Which option? Option 2. Okay. Now, this JEE Advanced 2024, leaving it for you. Why? Man, they gave potential energy as kr square by 2 da. Look at JEE mains 2019 question, kr square by 2. So basically this question, whatever I have done, the approach, will we have same approach here also? Obviously. And in fact, they directly gave the force also. They didn't make us calculate that force. Here they gave the force also. If you differentiate this, you'll get this only. So as it is a repetitive question, this has been asked in JEE 2024, JEE Advanced 2024. So I am leaving this question for you. I am leaving this question for you, as I already did a similar question. Okay. Now, man, I would like to, my tongue is twisting. So I'll just go have some water. I'm just giving 10 minutes of break because I was taking class from 2 o'clock. I'm taking class from 2. So my tongue is twisting. Right now the time is 7, right? So 7:17 I'll come. 7:17 the class starts. Just a 10 minutes break. And I'll tell you, these are the ones which are not mentioned in many of the books. It's important you also take break, but don't miss this part. See, I'll talk about effect of movement of the nucleus, because Bohr assumed that the nucleus to be at rest. What if the nucleus is going to be moving? In reality also, whether the nucleus moves, yes, nucleus is going to move, but it is going to have very small thingy. I'll talk about all those things, and then there is one more thing, something called as atomic collisions. So all of this will take around 40 to 50 minutes of time. Now you take 10 minutes of break. Okay, I'll be back. Good. So this class with 5 years PYQ enough for NIT. Pakka. Pakka. I guarantee that. See, man, I'm giving way good content. You can clearly, you should have realized it by now itself. Everything logically put, everything put one at a time in a sequence. After these classes, if you solve enough number of questions, you will get into IITs also. You'll get into IITs also easily. Okay, now, I have forwarded it. Let me just talk about the effect of movement of the nucleus. Okay, fine. Look, let us take, we have the nucleus here, Mn, and we have the electron, let's say somewhere over here, and the distance between them, let us take it to be r, that Rn whatever is there. Let us take it to be r. Okay, let me write it somewhere over here. Okay. Now these two are going to be rotating actually about their center of mass. Let us say that the center of mass is somewhere over here. So the nucleus will be rotating about the center of mass, even the electron will be rotating about the center of mass. So the path taken by the nucleus is going to be this thing, and I'll just take the radius to be some r1. And if I am going to talk about this electron is going to be taking a circular path about the center of mass, and let us take the radius of that path to be r1. And let us say some omega. They both obviously move with the same omega because they always lie in the same line. Only then the whole system can be in equilibrium. Same omega. Now you tell me, what is the total angular momentum, sir? When I am going to talk about the angular momentum about the center of mass is going to be MVR, right? What is the V of this one? R1 omega into, again, MVR, right? MVR. Yes. Due to the nucleus, man. Mn R2 omega into R2. Okay. Now look. What is R1 and R2? Can we calculate the distance of the center of mass? Distance of the center of mass from Mn. If you are trying to calculate the distance of the center of mass, you take reference as Mn. Then, if I am going to talk about distance of the center of mass from this nucleus, I need this, right? That means I'll take reference point as this. Then we have Me at how much distance? We have Me at r distance by the total mass. Okay. What about R2? You are calculating the distance of the center of mass from here. Oh. Shit. Sorry. I should write this one as, R2. I have taken it as R2. My bad, I'm very sorry. Very sorry. This is R2 and this is R2 and this is R1. This is R2. Now we need R1. So R1 is the distance of the center of mass from this one. So reference is this. Then you know the formula, right? M1 R1 plus M2 R2 by M1 plus M2 is the position of the center of mass, right? So when you talk from here, you have Mn at how much distance? R distance. Mn at R distance divided by the total mass, which is Me plus Mn. Now we have to get the total angular momentum, man. Quite a bit of calculation ahead of us. Okay, let us calculate what to do. So the angular momentum, if I write it properly, it is Me R1 square omega and it is Mn R2 square omega. And what is R1? It is Mn into R by Me plus Mn square omega plus it is Mn. What is R2? It is Me into R by Me plus Mn square omega. So if you look at, man, I can take Me into Mn out. Me into Mn out in the numerator, then you will have Mn plus Me as common and you will have R square omega divided by Me plus Mn square. So this and this gets cancelled out. So the angular momentum is going to be Me into Mn by Me plus Mn into R square omega. Man, normally what we have done in Bohr's theory is that we have taken the nucleus to be at rest. So the nucleus was at rest and the electron only was moving. Then in that case, it is MVR, right? So mass of the electron V can be written as R omega into R. So it is Me R square omega. This is what the Bohr has taken. But what is the actual angular momentum? Instead of Me, we have this. Actually this. This is equal to NH by 2 pi. What Mr. Bohr has done? He has taken it to be at rest and electron to be moving. As a result, the Me into VR came out to be this. This is what we have taken till now. Reality is this. Now some people might argue, saying that, sir, mass of the nucleus is way bigger than mass of the electron. So in that case, Me into Mn by Me plus Mn, whatever is there, is Me into Mn by, this can be roughly said to be mass of nucleus only, because mass of electron, whether you add it to it or not, it doesn't make much of a difference. Yes, then this value is roughly equal to Me. Roughly equal to, but not exactly equal to. That's why when Bohr has given his own theory, his values, do you remember in the beginning of the lecture I said approximately matched? I said I will explain why I use the word approximately matched with the experimental results. Why I didn't say exactly matched? It is because of this. Although this value is very close to Me, but it is not exactly equal to Me. And writing this is big, right? Isn't it scary also? So I'll represent it with a letter mu and I'll write the angular momentum as L is equal to mu R square omega. You people are habituated for this mu symbol. It is reduced mass. It is reduced mass. So if you look at the reality and if you look at the Bohr, wherever there is mass of the electron, you have to replace it with mu. You have to replace it with mu. Oh, that means Now everything is going to change. Bohr took that, reality is this. And what is the change? The only change is instead of mass of electron, you keep mu, you'll get correct answers. So which ones are going to get affected more? Which ones are going to get affected more? Let us talk about the kinetic energy. Let us talk about the kinetic energy. Man, I don't remember it. That's why I have saved it in my phone. I'm writing it. M e to the power 4. This is Bohr's. According to Bohr's. In this class only I have done it. In this class only I have done it. I can't go some 40 slides back and see it. So that's why m e to the power 4 by 8 h square epsilon naught square into g square by n square. This is the kinetic energy. Now, if I talk about the total energy, sir, what will be the total energy, sir? Total energy is minus m e to the power 4 by 8 h square epsilon naught square g square by n square. Man, this is what we have got in Bohr's theory. But reality is what? What is the reality? What is the reality? Wherever you have mass of electron written, replace it. Replace it with what? Replace it with what? We have to replace it with mu. So the reality, in reality, the total energy is going to be minus mu e to the power 4 by 8 h square epsilon naught square into g square by n square. Now we have one more thing. Already we have defined the value of this, sir. It is minus 13.6 eV into g square by n square. All of a sudden we have mu. So how to get the value? Okay, it's so simple. What we do is, I will multiply with mass of the electron and I will divide with mass of the electron. Then, if I am going to talk about this section, this part of it is exactly same as that of this. m e to the power 4 8 h square epsilon naught square z square by n square. So this part, this whole thing is same as the old one, right? So the real total energy, if I talk about the real total energy, in reality, the real total energy is going to be minus 13.6 g square by n square electron volt into, let us go back, into, so this we represented with minus 13.6 z square by n square. Now we have extra term mu by me, right? Into, so I will highlight that, we will have mu by me. Now look, I just want to see what will be the value of mu by me. Will it be less than 1 or more than 1? Let us go back. Let us see here. This value is more than mn. This value is more than mn. So mn by more than mn value. Or okay, fine. Let us not even talk about that. Here only we will put the mu value, sir. What is there? Here only we will put the mu value. Minus 13.6 g square by n square electron volt. What is the mu value of me into mn by me plus mn divided by me. Me gets cancelled out. So you get minus 13.6 g square by n square electron volt into mass of the nucleus by mass of the electron plus mass of the nucleus. So this value is less than 1. So the actual energy levels have a value which is going to be magnitudinally less than 13.6, because you are going to multiply 13.6 is less than 1. So what happens? So what happens? Look sir, according to the Bohr, the first one should be minus 13.6, the second one minus 3.4, right? But what is the reality? The reality, okay, wait a second. I'll talk about the reality. Here itself. I'll talk about the reality. So this is minus 3.4. Okay. Now, the reality I'll represent with blue color. Man. The reality is going to be minus 13.6 multiplied with less than 1. That means you might get some minus 13.5, minus 13.4. So minus 13.5, minus 13.4 lies where? They lie here. So if this is going to be the n is equal to 1 according to the Bohr, but the reality is the n is equal to 1 will be slightly above. So same thing happens here also. The n is equal to 2 will have slightly more energy than what Bohr has estimated. Okay. So this and all is fine, but now I have a doubt. We got photons, right? And the energy gap. If I take the energy gap in the Bohr's model to be x, and if I take the energy gap in the reality to be y, sir, which one will be more, sir? The energy gap in Bohr's model is more, or the energy gap in the reality is going to be more? Okay. So when I talk about gap in energy, gap, the Bohr, when I talk about the energy gap in the Bohr model, so the energy gap can be written as what? 13.6 electron volt into 1 by n1 square minus 1 by n2 square into g square. Now, if I talk about the reality, so the reality is going to have 13.6 electron volt into 1 by n1 square into 1 by n2 square into g square, but this is multiplied with what? This is multiplied with mass of the neutron by mass of the neutron plus mass of the electron, which is less than 1. So, if you are going to say this energy gap to be x, and in reality we are taking the energy gap to be y, so y is going to be what? This can be written as x, right? X multiplied with less than 1. So I can say that y is less than x. So if the energy gap is going to be less, then the wavelength will be more. If the energy gap is going to be less, then less energy photon will come. Less energy photon will have more wavelength. So the wavelength that has come out in reality is slightly greater than the wavelength that has come out from the Bohr's model. So slight deviation will be there. This is something which you people should know. For better conceptual clarity, if you are aiming for JEE Advanced, if you are thinking of tough JEE mains questions, you should have an idea about it. Man, very simple way to memorize it is going to be, see, wherever mass is going to be there, if mass is in numerator, you multiply it with mu by me. If mass is in denominator, then denominator you multiply it with mu by me. To the Bohr's model, you'll get the reality. Okay, super. That's why I said to you, right? whatever the wavelengths were given by Bohr, whatever the wavelengths which were given by Bohr, they didn't exactly come out to be same in the experiment. Experimental values were slightly higher to the Bohr's wavelength. Bohr said something, but reality is slightly higher. Right? Why? Bohr didn't take into account the movement of the nucleus. A very important thing. Now atomic collisions, man. This is one part. I think in 2000, 1 second. Just be there. Yes. JEE mains 2016, they have asked this atomic collisions. After that, they haven't asked. Right? And even in JEE advanced also, they were not concentrating on it much. Right? But yes, there is a possibility. Once asked, can be asked forever. Right? So we need to know it. That's the reason why I will cover these atomic collisions. But we have to start with an assumption. What is that assumption? If there is any 𝐂𝐤 loss, if there is any, what happened? Shit, man. If there is any 𝐂𝐤 loss, it will be taken by electrons and they go to higher excited states. This is one assumption which you people have to keep in mind. If there is any 𝐂𝐤 loss, that 𝐂𝐤 loss should be taken by the electrons and should go to the next higher excited states. If electrons are not able to go to higher excited states, then there is no loss in kinetic energy, indicating collision between particles, to be perfectly elastic. Only in perfectly elastic collisions only there won't be 𝐂𝐤 loss. Na? If there is 𝐂𝐤 loss, then it is not a perfect elastic collision, it's an inelastic collision. In perfect inelastic collision, maximum 𝐂𝐤 loss will happen. In perfect inelastic collision, maximum 𝐂𝐤 loss will happen. And I need to do a small recap of that also. So, in a perfect inelastic collision, okay, let me just take, you have M1, some U1 bar, and you have M2 having some U2 bar. The 𝐂𝐤 loss is going to be half M1 M2 by, see, I'm not deriving this, this is from your collisions chapter, like you can say center of mass, into U1 bar minus U2 bar square. Or for you to easily memorize, you can write half mu U relative bar square. Half mu U relative bar square. Okay. Now look. Zero kinetic energy loss in a perfectly elastic collision. Perfect inelastic collision will have maximum Ke loss. So no other collision can have Ke loss more than this. More than this. Now look, to understand what I am talking about, let me just take one small example. Let me just take some small example, man. With this example, you will understand every wording, whatever I have mentioned till now. Examples are the best way to understand the theory. Look, I have a neutron. I'm just taking a neutron, and this neutron is having some kinetic energy K, right? And I have hydrogen atom. What happened, man? I have hydrogen atom which is at rest. Hydrogen atom which is at rest. Okay. Now, if I am going to take the speed of this to be some u, mass of hydrogen and mass of neutron are going to be same. Hydrogen atom, I'm not talking about hydrogen molecule. Hydrogen atom and neutron are going to have same mass. Okay, fine. Now, for electron in hydrogen atom, to go, when did I put my marker over there? It detected some dot. Okay. For electron in hydrogen atom to go to higher states. Do you remember, man? If you don't remember also, I'll just draw it. See, from n is equal to 1 to go to n is equal to 2, what is the energy jump? It is 10.2 electron volt. To go to n is equal to 3, what is the energy jump? 12.09. Okay, sometimes they'll write it as 12.1 electron volt. 12.1 electron volt. Okay, now look. So the energy that should be given to the electrons, the energy electron should get, is going to be what? Either 10.2 electron volt or 12.1 electron volt or 12.75 electron volt and so on. These are the only energies electron can take. So when the collision is going to take place, loss in kinetic energy should be any one of them. Only then the electron will go to that state. If the electron is not able to go to that state, then the collision is not going to be perfect inelastic or inelastic collision. It will undergo perfect elastic collision. So this question can be asked, especially in JEE Advanced. They can ask this. Even in JEE Mains also they have asked. Now let me go further. Then I'll explain even deep. One more example. Let us talk about this situation only. We have neutron and hydrogen. So what is the max Ke loss that can happen? Maximum Ke loss is going to be taking place in perfectly inelastic collision, which is half mass of neutron. If I take m, mass of mass of hydrogen, I can take m only, by m plus n, into, as only neutron is moving, it will become u square. So this will become what? Half into half m u square or not? Half m u square is what? kinetic energy of the neutron. So now you tell me, what can be the maximum KE loss in the case of neutron colliding with hydrogen? It can lose maximum half of its kinetic energy. That too, when it will lose half of kinetic energy, when it is a perfect inelastic collision. When it is a perfect inelastic collision. Okay, man. What I mean? Look, I'll explain. For example, why so much of case 1. Case 1. Let us say the kinetic energy we have sent, like the kinetic energy, the K value of the neutron. K value of the neutron. Let us take it to be some 10 electron volt. Then what is the maximum Ke loss it can have? The maximum Ke loss it can have is when there is a perfect inelastic collision and it is 5 electron volt. Now look, if it is going to lose 5 electron volt, can the electron take it? No. So there is no point in losing kinetic energy. Who is going to take that? So for the energy to get conserved, collision in this case, the collision is perfect elastic. Why? This energy is useless. So there won't be any loss only. Because whatever the loss is there, it can have a maximum loss of 5. That maximum loss of 5 is not helpful for us or for the electron. As it is not helpful for the electron, then the electron is going to be like, man, whatever the Ke loss is there, that's not helpful to me. Then the atom and the neutron are going to be like, okay, anyway, I don't have enough energy to make the electron get excited, so I won't undergo any inelastic collision. I'll undergo perfect elastic collision such that there is no Ke loss. Peace. Okay, one more example. The case 2. The case 2 is I projected the neutron with 20.4 electron volt. Then what can be the maximum Ke loss? The maximum Ke loss can be half, which is 10.2. Maximum Ke loss can be 10.2. That means the electron can take that maximum loss and go to the higher excited state. Right or wrong? So for maximum Ke loss to happen, it should be a perfect inelastic collision. Collision can be perfect inelastic. Why? If it is perfect inelastic, only then the Ke loss will be 10.2. Only then the electron can take that and go to the higher excited state. You will understand even better with this example. Case 3. Let me just take case 3. Case 3. So let's take the kinetic energy to be some 21. Then the maximum Ke loss. Then the maximum Ke loss can be how much? 10.5 electron volt. But the electron don't need 10.5. It says, bro, if you can give me 10.2, I can go from n is equal to 1 to n is equal to 2. Then the neutron and the atom will decide and undergo an inelastic collision. Electron needs 10.2 electron volt to go to higher state. So the collision should provide, the collision should provide only 10.2. If collision is perfect inelastic, if the collision is perfect inelastic, the KE loss is going to be how much? 10.5. So what to do with the extra 0.3? What to do with the extra 0.3? Then the neutron and the hydrogen atom are going to be like, so let us not undergo perfect inelastic because the energy needed is less than what the energy loss is going to be. Then they are going to be like, they undergo inelastic collision, not perfect inelastic, inelastic collision. So what does that mean? So if you want to compare the inelastic collision, meaning over here is the coefficient of restitution is more than 0 and less than 1. If it is E is equal to 1, perfect elastic collision. E is equal to 0, perfect inelastic collision. But now they are going to undergo an inelastic collision where the E value will be between 0 to 1. What will be the T value? The E value will be in such a way that the KE loss, whatever is going to happen now, is going to be just a 10 point. The KE loss is going to be just 10 point. If it undergoes perfect inelastic, you are getting an energy which is more than what is needed. So then the atoms are going to undergo a collision where 10.2 will be given out. So coefficient of restitution will not be E is equal to 0 because it is not going to be perfect inelastic. If it is perfect inelastic, you will get 10.5, which is more than what is needed. So the collision will adjust the E value in such a way that the KE loss will be 10.2. Okay. Okay. Deepu fighting with JEE. Try that question. I'm giving all of these things, right? All these things have been given to you. You can easily fight it. Now you know the theory. Whenever you have these kind of questions, don't be scared of. As I said, look at the KE loss or look at the energy loss. That energy loss should be taken by the electron. That's it. That's it. So now did you understand? So basically, I have seen some people who are going to say that atomic collisions are always perfectly elastic. No, man. They can be inelastic and they can be perfect inelastic also. Now look, if you observe properly, with 20.4 itself, I was able to make the electron go to the first excited state. So giving beyond 20.4, also I can make it go to the excited state. But if you ask me what is the minimum energy to make it go to the first excited state, I don't need 21. If the kinetic energy of the neutron is 20.4, that's enough. Because 20.4 can have a maximum loss of 10.2, then it will undergo perfect inelastic collision and the electron will go to the higher excited state. So the minimum value of neutron's kinetic energy should be 20.4. Agreed? Minimum value is this much. So if it is less than this, let's say for example the neutron is having 20 electron volt energy only, then the maximum it can undergo loss is how much? 10. 20 KE means it will undergo 10, right? And is 10 enough to make the electron go to the higher state? No. Then waste. Then it won't undergo that 20 loss collision. It will simply say, okay, let us not waste any kinetic energy. We will undergo perfect elastic collision. When there is a possibility, only then they will undergo perfect inelastic collision or inelastic collision. Difference is there between inelastic collision and perfect inelastic collision. Perfect inelastic collision, KE loss is maximum. In an inelastic collision, the KE loss can be between 0 to KE max loss. Okay. JEE Mains 2016 question. That's what I have explained till now. A neutron moving at a speed v makes a head-on collision with a stationary hydrogen atom in ground state. The minimum kinetic energy of the neutron for which inelastic collision will take place is, what is the minimum? 20.4. Where is that? 20.4. If it is 21, yes, inelastic collision will take place. If it is 24, inelastic collision can take place. But the minimum where it started, at 20.4. At 20.4. Okay. Let me give one more small thing. Is it mandatory always hydrogen only has to be given? Can't they give something else? They can give. So you take the same story, man. We have, let's say, helium plus, which is at rest, and I am sending neutron only, and the kinetic energy of the neutron, I'll take it to be kinetic energy of neutron, I'll take it to be K. Again the same question, find minimum K for inelastic collision. So for that, first of all, you have to see how much the electron needs to go to the first excited state. First we have to see that. So Deepu, for you only I am giving this. For you only I am giving this. For you only I am giving this. And one more thing, I'll give you hint for you. Hydrogen atom changes its state from n is equal to 3 to n is equal to 2 due to recoil. The percentage change in the wave 26. See, one thing, oh, you're typing too much. Just tell me which year question. I'll take it up in the next class. You're typing anyway, I'm not able to understand. If Rydberg of emitted light is approximately, see one thing, you have an atom, right? And if the electron goes from n is equal to 3 to n is equal to 2, it throws photon. Photon has momentum, so the atom gains momentum. So when the atom is going to gain momentum, there will be a de Broglie wavelength associated with it. Might be you're talking about that. So you just conserve the momentum, you'll get the answer. Okay, fine. These are even more difficult than what you're asking. I gave you a hint, you try it. First state, n is equal to 1 state, is going to have how much energy, sir? Minus 13.6. Helium, right? 2. Meanwhile, please comment the mass of helium. Please comment the mass of helium. Okay. Minus 13.6, 2 square by 1, which is going to be minus 13.6 into 4. Minus 13.6 into 4. Let me just, my brain got saturated. Even easy calculations also I can't do. After teaching a lot in front of the lights, your brain gets saturated. If you ask a slightly tricky question now, I will not be able to answer also. Concentration levels. N is equal to 2. E2 is minus 13.6 into 2 square by 2 square, which is minus 13.6 electron volt. What is the gap, man? The gap, 54.4 minus 13.6, which is 40.8. So electron needs minimum. Electron needs minimum how much? 40.8 electron volt, something which is beyond 40.8. Right? Now, let me talk about the KE loss maximum we can have. The maximum KE loss we can have is when there is a perfect inelastic collision, which is half Who is that? Purposefully they typed it 7. Man, helium will have 4. Mass of neutron into mass of helium 4m by the total mass, which is 5m, into u square. So m can be cancelled out. So half mu square into 4 by 5. Half mu square is what? K. That's the kinetic energy of the neutron you are sending, right? So this Ke loss should be equal to at least 40.8. Then there will be excitation. Then you can say that there is a perfect inelastic collision. So in that case, 4K by 5 should be equal to 40.8 electron volt. So what will be the K value then? K is going to be 40.8 into 5 divided by 4. So 40.8 into 5 divided by 4, which will be 51. So if the minimum kinetic energy of the neutron is going to be 51 electron volt, then if it undergoes perfectly inelastic collision with helium, then the loss in kinetic energy it is going to have is 40.8. If the, once again I am repeating, last statement, with this we are done with the class. You people can solve all the questions of atomic physics and photoelectric effect and all those things apart from nuclei. Look, if the kinetic energy of the neutron is 51 electron volt, 51, if it undergoes perfectly inelastic, only then the Ke loss will be 40.8. If it is something else, then the loss will be less than 40.8. That collision is not possible. For example, to understand, let me give one more. The same thing. Ke loss is how much? Maximum Ke loss is how much? 4K by 5, right? 4K by 5. 4K by 5. So if I take the K as 55 electron volt, the maximum Ke loss you can have is how much? The maximum Ke loss you can have is 55 by 5, 44. But do we need 44? No. For the electron to go to the immediate next state, it just needs 40.8. So if you provide 55 kinetic energy to the neutron, then the maximum it can lose is 44. But we need only 40.8 electron volt. Then collision is inelastic where the Ke loss we are talking about is equal to 40.8. So it's not a perfect inelastic collision. It will undergo an inelastic collision where the loss is 40.8. That's it. How much hour is needed? That much. Okay, fine. With this, we are done. With this, we are done with atoms. Completely whatever is needed for JEE mains, and wherever needed, I have gone on the advanced level also. With this, we are done, and we have nuclei. What I am going to do is nuclei and semiconductors I will complete in 1 week. Nuclei and semiconductors will be completed in 1 week. So next week, what are we going to have? Next week, we are going to continue with the 11th one. Last week, I completed SHM, right? So the next week, I am going to complete waves. And the next week, I'll complete nuclei and semiconductors. Is Ke by Pe half? How, sir? I have already done it, right? I have already done it. Deepu, I have already done it. Just go back in the recording when I have done the Bohr's model. I have explained how the things have come. I have clearly explained. Go back in the video when I have done Bohr's model. Then I have derived the kinetic energy. I have derived the potential energy. Then I got the total energy. I have clearly derived and I proved it. So every time when you have a force which is proportional to 1 by r square, and if the particles perform circular motion, then every time total energy will be minus of kinetic energy or half of potential energy. No, you just go through that. You just go through. Please, Deepu, you just go through. I have clearly explained. You try it. If you don't understand, then you come in the next class. Then I'll definitely in the beginning, I'll do it. Only then I'll move forward. Okay? With this, because my brain is completely, what is that, fried out. Arey, just calculated it. Okay, rest of the people you can drop off. Okay, she is insisting. I'll just show. Look at this. I calculated the kinetic energy. How? First I calculated the speed of the electron in the nth orbit. Then I have used half m vn square. Then I have put the vn value. Then I got the kinetic energy to be this. I already calculated Rn value. In the previous slides, I calculated the Rn value, Vn value, everything I have calculated. Rn value I have calculated, right? So you put that Rn value over here, then you get the potential energy to be this. Now you see, kinetic energy is 2 pi square, potential energy is minus 4 pi square. So you can clearly see that the relation is like this, right? So from the derivation we found it. Right? I think it is clear. Okay, man, I don't want to waste time of others. Bye. Everyone, whoever, one last request. Everyone, whoever loved the content, whatever I have done, I have two requests for you. First, you like the video so that automatically the YouTube is going to promote the video and people will be able to go through this good content. Second is that if you have any friends who are struggling with physics, do let them know. It will be a good thing. Bye everyone.